Well, here we've got another pH problem, the third in this specific problem, and we're dealing with ammonia. And as we found out for our pH meter here, ammonia's got a pH that's in the alkaline, the basic section, where it's around 11. And if you'd put a pH meter in this solution, you'd expect the pH. In this case, we've got it to 2 significant digits. In terms of pH, the significant digits are only to the right of the decimal point. This actually acts as the exponent. That 11 will be an exponent. And with this, we'll want to find out how much acid is present, H+, what its pOH is, and what the hydroxide ion concentration is going to be. Let me flatten this all out, and that'll make things a little bit easier for us. Okay, in terms of my diagrams, and I'll get my text going. Well, let's see. The pH, we're given the pH, and we know that the hydrogen ion concentration is 10 raised to the negative pH. So I'll get my calculator out. Now, even before a calculator, I see that this is raised to about the 11. So this is going to be 10 raised to the negative 11, or 10 to the negative 12. That's the two values this will be in between. In fact, actually, we would end up then using our calculator. Let me pull up my TI. And this was 11.5, so I'm going to take 10 and raise it to. Now, if I put in 11.5, let me just do that just to show you how wrong this would be. We would get an answer for the hydrogen ion concentration as 10, this is like trillions of molar, and that's impossible. The concentration of the hydrogen ion concentration is going to be, and it's going to be 1 at the greatest. So let me clear that out. And when you do these problems, you should be able to sort of predict from a pH what your answer is going to be about. This answer for hydrogen ion concentration would be about 10 to the negative 11, 10 to negative 12 power. So I'll take my little exponent here, 10 raised to the x. Don't forget the negative. Don't use the minus, you use the negative, and that was 11.5. If you have a basic solution, it's going to be greater than 7. So we'll expect a small number, and we're going to get it. And here it is. I said it's going to be between 10 to the negative 11 and 10 to the negative 12, and here it is, 3.16. Now, we really should report that as 3.2 times 10 to the negative 12, but because of Webasine's error thing and such, we probably should type in the 3.16. And they wouldn't give you a problem with that on the AP exam if you carry to 3 significant digits. I get 3.16. Of course, it's not 3.16. It's times 10 to the negative 12. Oh, and don't forget, this is a molar concentration. I'll get my italics and type in M, molarity. So we would have this many moles of H plus in a liter of solution. That's minuscule, which is true. When you've got a basic solution, it drives down the H plus concentration. Just as before, we know we can end up finding the pOH pretty directly, and I'll get my calculator out and do that. And I'll figure that the pOH is going to be, and that was 11, I'll take 14, and I'm going to subtract 11.5 from it, and of course 2.5. Now notice, the smaller your value, the smaller your, in fact, let me get that up again because, yep, a nice even 2.5. Your p-value, the actually greater the concentration is. It's sort of a reverse arrangement, and we don't have any units. And that's one of the things you should be aware of whenever you're doing a p-value. The smaller the p-value, the actually greater the measurement is in real numbers because of that negative. And it would be nicer if they'd had left the negative there, but you'd be always typing in negatives, and they wanted to make pH simple so people wouldn't be confused. So that means you chemistry students will have to remember to put that negative in terms of understanding things. Now, we're going to, again, figure out the hydroxide concentration, and it's going to be 10 raised to the negative 2.5. So we know it's going to be 0.001 or so. So I'll get my calculator out. It's going to be a small value between 10 to the negative 2 and 10 to the negative 3. And always think about the values, because it's easy to forget a negative sign. And I'm going to take and change this p-value by knowing it's an exponent. And don't forget the negative, otherwise we'd get a large value again. And I'm just going to put in second function answer. I could have typed in 2.5 just as easily, but I calculated that answer. I've got a calculator that can use those answers, and indeed, we figured 10 to the negative 3 is 1,000th, 10 to the negative 2 is 100th, and this value is in between that. And I'll put this value in, and this is going to be a molar concentration. Calculator out again, 0.00316. And that is going to be in terms of molar, 0.00316. Oh, I was typing it in my calculator. Okay, let me type it in here. 0.00316. This is going to be a larger value because this is a basic solution. And let me not forget, because this is a real number. It means molarity. And so our hydroxide concentration, now this is pretty good for a hydroxide concentration. When you feel some ammonia, it's going to feel slippery, which is typical of a basic solution. It's not horrid. You can wash it, except I'd probably wear some gloves because it will take the oils off your skin. And did I put molar in there? No, I didn't. Oh, yes, I did. It just didn't show up here. There's the answer. And this is, remember, brackets stand for molar concentration. And in a basic solution, the hydroxide concentration will be significantly higher than the hydrogen ion concentration. Let me pull one extra thing up. I'll get my calculator out. Again, I'm going to take this and multiply it by 3.16, and I'll carry this out to 3. Second function, E negative 12. This was the hydrogen ion concentration. This is the hydroxide ion concentration. 9.992 times 10 to the negative 15, which is 1 times 10 to the negative 14. And that's what should happen. You should end up having both these values multiply out to make 1 times 10 to the negative 14. Because I rounded these off and didn't carry them out completely, it's not exactly, but it's going to be close. And that's true at room temperature. H plus times OH minus multiply out to make 1 times 10 to the negative 14. And of course, pH and pOH add up to 14. Oh, I just love logs.